Good morning, everyone. We're going to give folks a couple more minutes here, and then we'll hand it over to Bill. And then Bill will introduce today's presenters, and we'll get started. Still not seeing Travis, but he'll be with us just momentarily. Okay, we've got good participation today, 32 people on the line. Don't want to keep you, Bill. Others on from PNNL, are there folks on the line that can launch this before Travis arrives?
Sure, I can get us started.
There's Mark. Oh, excellent, Mark. Thank you.
Sure, I'll let Travis pull up the slides when he gets in. I'm sure he'll be here in a second.
Sure.
Today, we've kind of wrapped up towards the end of a study where we're looking at interregional transmission scenarios and evaluating their benefit or costs on a system scale. So this was a project funded through the National Offshore Wind Research and Development Consortium. We started about a year and a half, 2 years ago, where we're looking at 3 different transmission scenarios to interconnect offshore wind in Southern Oregon and Northern California. We'll walk through the scenarios in detail shortly, but the brief story is one of them looks at near term.
I'm just
2030
listening to a conference. I don't need to participate.
One of them,
dental insurance website.
Yeah.
And I
Jennifer,
the dentist's office again, and they say that I don't owe them anything.
Yeah.
Jennifer Mersing, would you please mute your phone, please?
Oh. Sorry about that.
so the first scenario that we're looking at is actually, you know what? I'll just pull up the presentation because I can do it.
All right.
And
Well,
then
while you're
we'll-
doing that, let me just invite
get
Bill
through the
here
first.
to say a couple things to get started.
Sure.
Bill Henry, you want to go ahead and take it over? I'll keep letting folks in the door.
Sure. Thanks, Jason. Thanks for joining, everybody. This is a meeting of the Pacific Offshore Transmission Solutions Work Group. We've been on hiatus for a little while, but we're going to have a series of very interesting meetings coming up over the course of the summer and the rest of the year. We'll kick this off with a presentation from PNNL today. In the future, we're gonna, in general, we're gonna tackle 2 different topic areas in the technical and technology challenges of this, which are, as we all know, substantial, and then also in the business model and transmission development areas to understand different possibilities for creating projects, sponsoring projects, and financing projects. So with that really simple intro, Jason, if there's no other comments to make, we'll hand it over to the PNNL team. Looks like we got Travis on the line now. We'll hand it over to Travis, Mark, and the PNNL team, and they'll introduce themselves and the team on the call today, and go forward with the presentation.
Great. Bill, can you hear me okay?
I can.
Yes.
Okay. Super. Well, good morning, all. Yeah, let me try to share my screen here. We do have the whole team on the phone, which is great. Let's see. Great. How is that looking?
There it is. If you want to do full screen, there it is. Perfect.
Looking good? Okay, cool. All right, well, yeah, let's just hop into it. Sorry, I'm a little late from another call. But yeah, this is the list of team members here on this slide. This is the title of this project is Maximizing Electrical System Benefits of Offshore Wind Energy in Southern Oregon and Northern California. I think some folks on this call are familiar with this project. We've talked to you a bit about it over the past 18 months, but it has been some time. So here we are at kind of the tail end of the project, and we wanted to give you a readout on our latest results and give you a recap of the work as well. So what we will do, I think, Perhaps we'll have a few different speakers. Not everyone listed here will be speaking today, but you're going to hear from Sahom and Lee and Shanawaz and Mark. So maybe that group of people can give a quick introduction before we dive in. But
Is
yeah,
it going to be recorded? I'm sorry to interrupt. Is this going to be recorded?
Yeah, yes, Carl, it will be recorded. And as with all of our recordings, they'll be posted on the POTS website, which you can find a link to at the very bottom of POET's website. Simply says POTS, click on that, and that will take you to the POTS website.
Okay, super. Well, I'm Travis DeVille. I'm the Wind Energy Systems Integration portfolio manager here at Pacific Northwest National Lab, and formerly of the wind energy industry, and have done some research in this in the floating offshore wind world, but also fixed bottom offshore wind world, all around grid integration of large amounts of offshore wind energy. So we're talking gigawatts of in basically the Atlantic and then in the Pacific context. So let's head over to Sahom. Maybe Sahom, a quick intro.
Thanks, Travis. Yeah. I'm Soham Datta. I'm a power systems research engineer at PNL for the last 2.5 years. Primarily, I work with transmission system planning and power system modeling. And in this project, I have been helping Travis out with some of the electrical and the power system studies associated with offshore wind integration in the West Coast.
Thanks, Sahom. Lee.
Hello, everyone. My name is Lee He, and I joined PL 10 months ago, and I have been working on this project since the first day I joined. So yeah, I have been working with Travis on the production cost modeling and the power flow for this project. Thank you.
Thanks, Lee. Shanawaz. If Shanawaz is there, maybe he's not on or not unmuted. Let's go over to Mark.
Hi, everyone. Mark Severy. I'm an engineer at PNNL. I work on many different aspects of offshore wind, including transmission, environmental impacts, and a few other things. I've been working on this transmission problem in particularly in Northern California and Southern Oregon for the past 4 or 5 years. So happy to be a part of this study.
Great. Thanks, Mark. Shanawaz, I see you there. One more time. Give it a shot. No, I can't hear you. Sorry, Shanawaz. We'll come back to you. I want to acknowledge also that I've got my colleagues from Hitachi here. So we've got Jinzu and I believe Steven's on. And if you guys want to say anything real quick, because you might talk as well.
This is Jinju, Hitachi Energy, and I'm the consulting director for the economic study group. Thank you.
Thanks, Jen. Steven?
Hi, this is Steven. I'm in the Hitachi team. I did the data processing and the visualization and analyze for this project. Thank you.
Great. Thank you so much. And Hitachi's done some really great work on the capacity evaluation, so we'll get to that later. And then, of course, Bill and Jason, they're actually part of this project. They're not just, they've helped us a lot on, working with you folks and getting your input. So acknowledgements to those fine gentlemen. The agenda is to give you an overview of the project, to go through some of our methods, which also gives a chance to talk about these scenarios. We have done that in the past, so we're going to try to move pretty quickly through that stuff and then get to the meat of it, which is the valuation and some of our preliminary findings so far, and then to have a discussion around those findings and indicate next steps for this work, not really for this project. This project we're kind of at the tail end of the project, but as with any project, you learn things and things you'd like to do in the future and things to explore further. That kind of a conversation will happen at that point. Okay, so here's the study. It's an 18-month study. The idea is to look at truly an interregional benefit of this compelling resource off the Southern Oregon and Northern California coast. A lot of people on the phone are tracking that quite well, I think. So we started January of 22. We optimized generation footprints for system value. And this valuation wheel in the lower right kind of gives you an indication of what that valuation scope is. We really are focused on the grid value. We're focused on, for example, energy, of course, delivery and capacity contributions to the overall Western interconnection, but then also grid support services, frequency response, regulating reserves, contingency reserves. Some of these things that are somewhat operational, we want to try to think about that even in the planning construct where we cite this. It's pretty much an open slate. So, why not clean slate? Why not think about these things now if we can, and try to identify, ways to optimize that value. That was kind of the inspiration for the project. It was kind of born out of something we saw on a former project, as I mentioned before, where we saw a very energetic Wyoming resource, which required a lot of ramping reserves to balance out the volatility of that resource. And we thought, well, gosh, if you blow that up at scale, you see, if you just chase energy, you might end up, particularly in a decarbonized grid of the future, requiring a lot of support services that are harder to come by. So that's really the kind of the fundamental driver for this work. We also look at benefits on the transmission system in terms of congestion relief, transmission expansion, upgrades incurred or deferrals of those upgrades. So these are net valuations, net benefits. So we're looking at benefits and costs, and then taking the net of those, and we actually end up looking at that on an annualized basis. Of course, we look at things that matter a lot to the coast, like reliability and resilience, but they also matter to all of us under certain, resilience, plausible resilience futures. And then also, when we think about the transition that we're all undergoing on the grid here to a heavily decarbonized asynchronous type of generation. And then finally, we do make a few exceptions, not purely grid, because what's going on with the grid is all driven by the environmental benefits. So we'd be remiss to not include that. And that's something we've indicated from the get-go, that we're looking at criteria: air pollutant, avoided air pollutants, and carbon emissions that are potential benefits of this, this switch to a different type of generation mix. And I actually thought Jason said that best when, a few calls back, when he said, the climate change is the challenge of our age. And I've quoted you numerous times, Jason, and it forces us to do things we otherwise wouldn't have done. And when I think about what we're talking about here, floating these multi-ton structures, it's just the engineering complexity is off the charts, right? Why are we doing this? Well, that's, I think Jason's statement sums it up really well. So it's important to include those benefits. And then there's also, associated with that is there's this hedge value benefit. Our economists tipped us off to that, Dan Boff, early on. So if you don't have to procure or plan on the volatility of a fuel that you'll have to purchase in the future, the volatility of that price, if you don't have to plan for that, there's a savings in addition to just the not having to buy the fuel. Okay, and we're looking at 3 conceptual transmission scenarios that go with that, and I will introduce those to you shortly. But fundamentally, what grounds all of our work is this, and this is something we've learned as we've waded in here. This is not our first study off the West Coast looking at offshore wind, but we've gotten a little smarter. I think we've made an effort at least, and we've been advised by people like those on the phone where, it's not simply about top-down targets. Like, I know policymakers have to list, a certain gigawatt capacity in a piece of legislation, for example. That's a useful thing to do. But as planners and as researchers, our job is really to think about what can that grid today. You don't start over with a new grid, right? Building the grid is quite expensive. It's complex. There's many potential hangups. So this grid we have today is very valuable. It's the result of a lot of such studies like this and heavy investment over many decades. So
Wes White, would you mute your phone, please?
Okay, thank you so much. So yeah, it's important to us to think about working with that grid that we have today. So this means starting with onshore POIs, points of interconnection. That's what we've done the whole time. We start there, we look at that onshore grid, and we do things like run a production cost model, or we use, and this is some of the work, so Lee has been kind of point for us on the production cost model. Shauna Wass has done some of these DC contingency sweeps, so direct current under direct current assumptions, but looking at, what would happen if you were to lose one line, and what kind of upgrade would you really need to plan for, given that the system has to perform under contingency conditions, and those are DC. Later we come to AC. So we start with onshore connection scrubbing, and then we look at potential resource and the resource addition. So generation design to match that capacity, and then transmission that goes with that to bring it to shore. The third box here is then to consider not just the grid we have today, of course, but what does this offshore wind do to that grid, and how does it alter the dispatch? And we do that on two different horizons in this study. We do one near term and we do one more heavily decarbonized into the future. And then importantly, we take that dispatch, the 8760 hourly dispatch, and we say, which is done under DC power flow assumptions, which is a major assumption. And we say, no, and this is again, Shanawaz led this work. Let's take an hour of interest, say a high wind hour or high load hour, or a low wind hour, or low load hour. Let's pick those hours of interest and then bring those into the alternating current power flow domain and run very detailed contingency, voltage stability, and dynamics assessments of the grids that are going to support those flows. And then we come back, we identify upgrades based on that work that are needed on the system, just like a true system planner would have to do. And then we put those upgrades back into the PCM and rerun the dispatch. We also look at performance under a variety of conditions. So there's the business as usual, but also what about resilience events and what is the capacity of this resource in different times of the year when the net load peaks are high in different regions. And then finally, we value it all. And that's an application of that valuation wheel. So of course, we use the dispatch simulations. We also do a separate capacity valuation, which we're excited to tell you about today. And we carefully consider power systems impacts. But it's key to also indicate here that we do things at system scale. So this is not the kind of valuation that you would do as a project developer. It's not, the kind of valuation, and I mean by that I kind of mean a generation project developer, but it's also probably not the kind of valuation you do from a transmission developer perspective. This is really our audience here, although informed by you folks, is policymakers. Where should the next call area be? How should we invest as a society in harnessing a resource like this? So in one slide, these are the three scenarios that we've put together. And when I say scenario, I mean a combination of generation and transmission and a certain state of the Western interconnection represented in that same scenario. I'll read from left to right, and this is just one slide, so we'll go into these in more detail. But the first one we're calling the 2030 HVAC high voltage alternating current radial interconnection scenario. So this is the most simplistic one that folks probably are already thinking about or have seen us present in the past, where it's just generator lead line type radial interconnections. This is likely what's going to happen first. This is what's happening first on the Atlantic. And so we tie these to the call areas that we have today. But we pick those where we think there's transmission capacity today as well, which is why Humboldt is now called out here. So we focus on Brookings and we really focus on Coos Bay, because that's where the capacity, that's what the POIs tell us the offshore wind can come from most easily. And then in the future, we call these 2030 plus scenarios. So these are beyond 2030, clearly beyond the 2030 anchor data set, because we put an additional 35 gigawatts of variable renewable energy resources, primarily land-based wind and solar, onto the system. But there is about 3,800 megawatts of Diablo Canyon offshore wind in that base case as well. And then we also include scenario one. We include those radials running from the Coos Bay call area and the Brookings call area. And then we do include one more change from the California ISO transmission plan 2122, which I'll show you in a moment here. On top of all that, we add 16.3 gigawatts of installed capacity. And by the way, that brings the total to 20.1 gigawatts total on the West Coast in this scenario. We look at that from two perspectives, and the one in the middle, the 2030 plus HVDC. So now we're high voltage direct current radial interconnections. That's the middle scenario. And then the last scenario is to tie those together in the ocean and form a multi-terminal DC, MTDC backbone. So that's what we're going to talk to you about today. So here's the first one, 2030 scenario. These are the HVAC radials. This supports 3.4 gigawatts of installed offshore wind capacity through Oregon and points of interconnection. You can see the breakdown of the power flows here in the lower left. The wind roses are kind of north-south, which is awfully convenient for a researcher trying to draw parks in the ocean. But I will say the one key piece of this is that, and one thing that differs in the way we plan this transmission is that we have not assumed 500 kV builds. So we've tried to look at this as a 230 kV or less development of the system, and using just taking the centroids. It's simplistic in the generation piece. You know, we're looking at kind of average wind production over the entire call area, taking it at the centroid. So we're doing that in Coos Bay and in Brookings. And then we're either assuming a nearby POI like Wensden or Rogue, or in the case of Lane and Dixonville, we're actually running 230 kV across to that I-5 corridor. And so those are major builds. Those are brand new double circuit 230 kV overland builds that we are including in this scenario. And those are not so different than the builds that are there today. Okay, when we go to beyond 2030, we have a different base case. So I should have said that here in 2030, the base case, so we always need a comparison point. So we want to see, like, what is the value of the HVAC radial scenario that supports 3.4 gigawatts of offshore wind in 2030? What do we compare it to? Well, we compare it to the WEC 2030 anchor data set. So that's been our base case for this first scenario. And then when we get into the second scenario and the third scenario, we use the same base case between those two, but it's different than the anchor data set. It's not just the ADS. We start from there, but then we add all these additional onshore, primarily onshore wind and solar resources. And then here's the CAISO change that I alluded to earlier. We include a new Collinsville substation and a 230 kV link to the Pittsburgh substation that exists today already. And that's an important way to move. And that upgrade was targeted for capturing North Coast offshore wind. So that's an important one to include in our model. Excuse me. So then here's the 2030 plus, or beyond 2030 HVDC radial scenario, which supports 16.3 gigawatts of offshore wind. And that's about 12.9 gigawatts of brand new stuff that's not in that scenario one, in that first HVAC radial. So beyond, so all the stuff coming off the purple 230 kV runs, those are radial lines, and there it's totaling about 12.9 gigawatts or so. So here's how that breaks out. We end up putting 2.7 gigawatts to Southern Oregon, 1.8 gigawatts through Humboldt. We do a run up north. So actually have some offshore wind going into Washington and Grays Harbor, and then also in Portland for a total of about 3.9 gigawatts. And then we send quite a bit south into San Francisco. And that was one of the reasons why BOEM funded the study. We were asked by an RDC to map the power flows into San Francisco, and we worked with BOEM to make that happen. So that's an important focus. We also optimized this generation footprint for capacity and energy value, and then applied kind of least cost transmission design to that footprint. I'm sorry, I'm going kind of fast, folks, but we have a lot to tell you about today. Here's how this is what the kind of more detailed, it's kind of a cartoon sketch of what the HVDC radial scenario looks like. So we end up putting HVDC converters in the ocean, and we run radial lines to HVDC converters that are based near these points of interconnection that have capacity. So SATTOP is the farthest to the north near Grays Harbor. Alston's in the Portland area, as folks know. We end up using, and this was an adjustment we made, we end up using the existing 230 kV system to move the power to Trojan. At first, we had a separate converter there, but we realized that it wasn't much power we were putting there. So we, just based on economics, it made sense to just stick with one converter. And all of a sudden, these converters are extremely expensive. It's incredible, $275 million a piece. So we try to really avoid the blue triangles wherever possible. Then we have flows into the San Francisco, and it's not a very accurate drawing here, but in general, with the Potrero substation is the major substation in the San Peninsula. We put power directly through there and then pass it on to converters in San Mateo and Martin also in the Bay Area. And then we run another line into Tesla. So we're not just hitting San Francisco, but we're also trying to go beyond that and Moss Landing. All right, now the backbone. So how do we do this backbone? Well, we basically have the exact same power flows, exact same buses of interest. Everything's the same about this scenario, except that there is a link now in the ocean. So if you had a one-line diagram, it would look like this. You know, you have these buses are able to, these converters are able to send power between different nodes in the ocean. And then there's multiple connections. So actually Trojan is lumped into Alston. So it's 1, 2, 3, 4, 5, 6, 7 different connections to shore on the backbone. So if you think of an actual backbone, you know, you've got your, I mean, what does that leave me with? 6 different vertebrae there to send the power to shore. And then how do we size that backbone? Well, that was tricky. And the way we went about doing this is we linked these nodes in the ocean. So again, remember Trojan and Alston, that's kind of the Portland node. That one is kind of becomes all through one converter because we end up using the existing 230 kV in a Portland hub. So we don't need a separate converter from into Trojan. So we have that one at the farthest north, and that's where the least cost transmission per megawatt puts that park the farthest north in the ocean. Although these are all pretty close together. Satsop, which goes all the way to Grace Harbor, is a little bit south of that. And then the San Francisco set of, you know, the converter that sends all the power to San Francisco is south of Satsop. So that's a key link, Satsop to the Potrero, Martin, San Mateo. This is the north-south, kind of the key. Like if you want to track the north-south flow, these are the northern POIs, and everything south of this is the southern POIs. And so that's kind of an interesting one to track, and you'll see presentations of that today. Moss Landing and Tesla then follow to the south. What we did is we had these 12.9 gigawatts of offshore wind from the radial scenario, the 2030 plus HVDC radial scenario. And basically what we did is just connect those converters together in the ocean, and then we ran an unbounded case, and we ran you know, the production cost model, hourly dispatch, unbounded, and we observed the load flows, like how the system wanted to use that, because the you know, the MTDC is clearly not going to be used just for moving offshore wind, and that's a lot of the value of it, right? Is how can you use an asset like this for other purposes to deliver other benefits? So it was important to run this unbounded case to understand how the system would use something like that. Once we saw what the flows were on the individual links, and here we're just one example, we're just showing this, I guess kind of hard to see here, but it's this Portland to Satsop, Portland hub to Satsop link in the backbone. Here we look at the unbounded case, and we plot the load duration curve, the absolute value of the load duration curve actually. And we see, okay, what we'd like to do is not just oversize this thing, not make it the most expensive, you know, it's already plenty expensive. So we want to try to be smart about the sizing, and we don't oversize it. So what we've done here is we try to target this U90 of 10%, which is roughly what we see for the DC intertie onshore from this WEC transmission adequacy page. And so what we sought to do was say, okay, don't actually build out 6,000 megawatts of capacity on that link, because there's only 3 hours of the year where you use that much capacity. Really, what you'd like to do is you know, make an investment that you use most of the time, but sometimes you maybe are curtailed, and sometimes you can't support, you know, you can't support infinite flows on that one link. And we did that throughout. We did that for every link. We did that for the links to shore. We did that for the links on the backbone. So in this case, we also think of, you know, what's out there today. We assume a 2,600 megawatt capacity of a 500 kV HVDC bipole subsea cable, which is existing today or on the, you know, in the near future. And we say, okay, on this one, we'll just stick to that 2,600. If there was a really high flows and for a lot of the year, like there are between Satsop and Potrero, Martin, San Mateo, then we do, okay, we'll do 2 of those. We do a 5,200 megawatt capacity. So that's how we went about sizing this. And we didn't quite end up at a U90 of 10% because there's some couplings. It's probably a little bit more constrained than that, but the key was to not oversize it. And that was what we're really trying to do. And then what adjustments did we make? So here you can see that when we first, you can see less converters. You might notice that. So in the San Francisco area, we put in a hub. And the idea, the reason for that was we started with multiple converters from scenario 2 and linking them all together. And we started to see looping. We saw looping on the HVDC backbone, so that the same hours you'd be flowing offshore wind into Potrero, you'd be sending power from somewhere else on the system, from San Mateo back to the backbone. Didn't make any sense, right? You would never want to. You would never want to design a system that loops like that. It's just you know, incredibly wasteful. And so we went to this. We went to an AC hub concept in San Francisco, and this is not that different than what you see in the CAISO transmission plant. So we understand why they do that now. It makes a lot of sense. Yep, and those are the major changes. So there's actually less converters in this scenario than there are in the HVDC radial scenario. But I did put in some pause breaks here. Bill, we didn't talk about this. Jason, I know we didn't talk about this ahead of time, but I want to make sure we don't just go way too fast. So
We did have a question.
Yeah.
Pulling this up now. Travis, in the multi-terminal linked layout, is this a ring bus on the platform at sea so that power can move between platforms and export at the same time?
Yeah, that's the assumption. That's right.
And then if you look in the chats, Theodore has provided that. He posted the question as well as some graphics there, the schematic if folks are interested. Not seeing any other questions. Regarding presentations today, of course, the recording is made available to you on the POTS website. I put the link in the chat. And then Travis, will you make this presentation available for folks?
Yeah, we will. I'm just I'm still getting it through our internal release process, so you're kind of seeing a pre-copy. But yeah, I think it won't be a problem to get you the charts. We have, as you can see, 106 charts here. We're not going to show all those today, and a lot of those are backup. So the copy I'll send will probably be a subset of this.
And we also have a question from Talia Kruger asking about what are the cost ranges?
Great question. We will get to that. We're going to show you the cost breakdown for this equipment.
Okay.
On a future slide.
Abraham has a raised hand.
Sure. The question I have, Travis, is some of the questions that we have in our studies, the maximum capabilities and so on, and we try to work with OEMs, and this is a very evolving the kind of field. Every few months the numbers will go up. But based on our earlier discussions, our understanding was that subsea HVDC links, because of the DC cable limitations, is kind of a 2,000 megawatt. And I was wondering if the assumption here with 2,600 is that development is going to happen, or are we assuming like two cables in parallel? Any insight to that would be great.
Yeah, great. Thanks, Ibrahim. Really insightful question. Yeah, I think 2,000 is the capacity that I hear about today. We are leaning a little bit on this assumption. We are assuming that Nexans has made some announcements about a 2,600, but capacity in the future. It is a single cable assumption.
Okay.
Yeah. But where I've drawn, this is kind of a rough cartoon, apologies, but where I draw two in parallel right next to each other, that's supposed to mean two of the lines for a total capacity of 5,200 megawatts, for example.
Okay, perfect. Thank you.
Yeah,
Travis, we have some other questions here. Let's see. In your earlier slides, you showed radial connections. What happens to this transmission that's infrastructure going forward?
Does that mean going forward in time?
Yes. I mean, if you, I think the concept there is if we build radial lines, what happens to those moving forward?
Yeah, great thought. Let me go back here. Where's the graphic? Here we go. So it's hard to see here, but we've kind of, we have intentionally stitched these HVDC radials through the centroids of the call areas. And remember, that's exactly where we put the HVAC radials running from in Coos Bay and Brookings Call. It is not hard to imagine. I think it would probably be pretty beneficial to think about kind of a master collector system to allow even flexibility of that power to move north-south and not just through the radial interconnection. It's a great question from Ross. We didn't focus on that in this study. We're trying to get our hands around a lot here. So we did not study that, but we did think about that. And we would love to study that in the future. But yeah, I think it's important to think about. It's kind of like the mesh ready conversation in New York, right? Like what happens to these things over time? And can we make use of this large investment, by extending it in the future?
A couple more here for you, Travis. Eric asks, using the AC 230 kV system presents some limitations. What is the maximum injection amounts that you plan on that system?
For the AC case, 2030 HVC radio, the max injection here is 800 megawatts into Lane or Dixonville.
And that would be on 2 circuits.
Yeah.
And I see Carl has his hand raised.
Yeah, thank you. I think the background idea is really clever, similar to what was proposed on the Atlantic side originally. I have a question just about expansion of this. You know, we have these enormous climate goals in each of the states that we're looking at, and a real great opportunity to add a lot of megawatts and a lot of constraint on the terrestrial side to get lines built. Is there a plan for, I mean, I'm looking at 2030 scenario, that's only 7 years from now. Are we going to look out further than that? I mean, in California, they're looking at a 20-year plan, much further out in terms of what we should be looking at. They're not doing it as well as they should either, by the way. But it seems to me that we should be thinking longer term and bigger capacity. So how expandable is this?
Well, I think it's just a function of I guess how much you want to build out that backbone. So when we built that, what I was trying to show is that we were pretty careful not to overbuild it, to oversize it more than what the system today more or less uses. And I should say, when we ran this unbounded case, we did that on the future system. So that's with 50 more gigawatts of VRE. Now we need more than that. I mean, we're going to go beyond 50 more gigawatts, right? So you could make the case that this same design exercise should happen at an even further stage. What you could do potentially, if at some point you run out of, I don't know if we'd have modular converters, like if we could add to those in the future, you could run new lines between converters, but the converter capacity might become what you choose to do in 2035 by putting a converter out there might limit you in terms of how upgradable that system is in the future. This is the same problem with POI upgrades. Like, you know, should we help people invest for, you know, digging up the beach only once, you know, so we don't have to keep doing that, keep disturbing things? Could we somehow figure out a mechanism so that, you know, because the project developer is not going to do that, right? They want to land their megawatts. That's it. You know, they don't really care about the next 5 projects. But yeah, I mean, it's a question. You could, if we could align as a society, then we could potentially invest in higher capacity earlier and use that as an upgrade later. Maybe that's unlikely, and then in that case, you would need to put another converter out there if you wanted to add a lot more. Yeah.
So one last question here. It says, I don't see any future generation coming off of the Del Norte coast. Given it may be one of the larger generation centers for the California coast, how do you propose to transmit power from that area?
Yeah, I mean, you know, something like this could be done there too. We didn't include that because we just did that optimization one time. Certainly could be. I mean, this is all running right through there, right? So if you look at the like the tail end of our optimum footprint is still north of the southern end, I should say. It's still north of the California-Oregon border. But, you know, this could stretch, and there could be really good arguments in terms of diversity of resource to stretch this shape and to look at other, maybe they don't all need to be adjacent, you know, but you could still run a backbone through them potentially. The costs do go up a bit, but, you know, you're already incurring a lot of these cable run costs to go that far anyway. So why couldn't you pick up offshore wind in Del Norte? I think you certainly could make that case. It's just not what our optimizer put out this time we ran it. But that doesn't mean it's not worthy of consideration. I should say there's a lot of stuff we did not exclude in this optimization. You know, we didn't do anything about, we didn't look at anything but except for the wind, basically. We looked at transmission capability and we looked at wind speeds and put it through a power curve. And we looked at 20 years of data. And this is kind of where the wind wants you to put wind turbines. But it doesn't really mean that that's the best place to put it overall. But it's what we—
Travis, just to add on, I don't think the points of interconnection in our study would change based on if the generation footprint was shifted south a little bit.
No, they wouldn't. Yeah, right. So this whole backbone would just kind of extend, but the extensions to shore would be the same. So in other words, I think what you're saying, Mark, is you could stretch this and it could account for offshore wind out of Del Norte.
Okay, I don't see any other questions. You want to go ahead and proceed?
Yeah, let's keep going. Thanks, folks, for asking all those questions. I hope that kind of whet the appetite. We're going to get into some results here, and we wanted to, before we did that, provide some assumptions. And I think, Mark, we're going to pass this over to you.
Yeah, I'll just cover this one, then ship it right back to you. So just some assumptions going into the technology and economic valuation here. So we're using a discount rate of 7.25%. That's a discount rate we pulled from utility resources that are using that. The lifetime of the wind plants is 30 years. The transmission assets are 40-year lifetime. Capacity of different lines that we're building. So we have 230 kV circuits at 400 MVA, and then subsea bipole for HVDC is 2,600 MVA for each 500 kV circuit. Getting into the costs of the transmission equipment, we're pulling all these costs from a JEDI model. It's a tool that's freely and publicly available. And we used pretty conservative build assumptions there. So the costs, there could be flexibility up or down based on the numbers we're using. And then throughout, we're modeling a per year valuation. And we assume that the generation and emissions are consistent over that entire lifetime of the project. So we can really pull any year of the project and it would have the same value. For emission costs, we use the social cost of carbon from the Biden administration at $89 a ton. So this is a number they put out recently. And then for criteria air pollutants, this is really a public health value that's put out by the EPA of how they value emissions reductions for NOx, SOx, and PM as well. So that covers most of the costs. And then importantly, part of our model includes the evaluation of extreme events and how this impacts the transmission scenarios we're looking at. And we model a combination of 3 different extreme events: heat wave, wildfire, and drought. The probabilities of occurrence and the type of event are described in here, and we'll talk about those a little bit more in detail later. But heat wave would occur every year, be 3 days long. Wildfire along the California-Oregon intertie has a 6% chance of occurring right along the line. And then drought, which changes the hydro dispatch in the Pacific Northwest. We're using data from 2001, which is a 3 in 21 year chance of occurring. So some of the assumptions we could I'll pass back to Travis to go through some of the key findings up front and talk about the overall results.
Yeah, thanks, Mark. So yeah, here's some key findings, folks, and we're going to show you these in just a moment. We want to make sure we put this up front so you see it. What we see when we look at this, applying this system-wide valuation, which is informed by all these different analyses, both from the production cost world and the AC power flow world, some of these, the associated system capacity contribution, which we'll talk about shortly. We see positive net benefits for, we varied carbon costs, we varied heat wave probabilities, and then we varied an HVDC cost factor, because we don't have a good, really sharp sense for how much HVDC subsea equipment is going to cost, or even floating HVDC converter stations. We really don't understand that. So we applied to date, that's probably future work, but we applied a variation on the cost that we have today out of the JEDI model, and scaled those up between an additional 25% and an additional 100% of the cost that we have from that JEDI model. And the carbon costs were either, as Mark just talked about, the Biden administration number or the later EPA released cost of carbon. And then heat wave probabilities varied from, every other year, 3-day heat wave happening in the Southwest to 4 times a year. So these were the variations we ran through the valuation tool. And we found positive net benefits for every 2030 HVAC radio offshore wind case. That's the first finding. Then the second finding is that for certain combinations of carbon costs, high resilience or resilience probabilities, and HVAC cost assumptions, we found positive net benefits for the 2030 plus HVDC radio and the multi-terminal DC backbone case. And the backbone helped deliver positive net benefits more scenarios that we ran than others. In fact, it increased the value of offshore wind generation by 375% in the standard case, which is a heat wave every other year, lower cost of carbon, and a 25% increase in the HVDC technology costs. So an additional 1.4 billion in annual incremental net benefit from the addition of the MTDC. And then every case, if we look at the high carbon cost assumption from the EPA, for us, it was the high one. It wasn't the highest one in their reports, but we concluded that every case has at least a benefit cost ratio of 1.5. The benefit cost ratio also is better earlier. So that's something interesting, that over time, there is an erosion of the per megawatt benefits. So in terms of energy, capacity, hedge value, for example, also congestion gets worse as you put more and more offshore. I mean, it probably is not a surprise. As you put a ton of offshore wind on the system, eventually congestion picks up. The transmission expansion cost goes up quite a bit per megawatt. So just a thought, this isn't really based on the analysis alone, but these early gains could be targeted in a strategy that seeks to deliver value to coastal communities in exchange for a long-term play to provide some of these interregional electricity benefits. That's an important thing to see, this kind of change in the value as we look at the near term and the near future versus the more distant future of the Western interconnection. So without delaying it any longer, we'll dive into these. And Mark, did you want to take the first two of these?
Yep. Hey, Andy had his hand up momentarily. He might have already taken it down. Sorry.
Hey, I just didn't understand that last point. Maybe everybody else did, but it's counterintuitive to me that the benefits erode over time. Because I would assume that a lot of the sort of costs surrounding a project like this would go up. You know, cost of electricity, cost of carbon, increased congestion. So why, I don't understand the erosion of the benefits. Sorry if I missed it.
No, it's fine. So this would be looking at, like, for example, the value of the increment in energy when you add an increment of offshore wind, and then you normalize that by that increment. So
okay.
It's still valuable. It's not that it's not valuable. It doesn't mean that the energy is 28% more expensive
Per incremental megawatt, though.
Yeah, it means what you get today for investing in that, well, putting the cost aside, if you just put in, well, including the cost actually. So what you get today by putting in 1 gigawatt of offshore wind buys you a certain amount of energy value, right? But if you make that same investment in 2035 and beyond, or say, make closer to 2040, you won't get quite the same system value out of that.
Okay.
And this is not, I shouldn't have probably used that example because that makes it sound like what a developer would do. But I really mean in terms of the overall system. A classic one is capacity. So, we know that initially you add a new type of resource to a generation mix, and as long as it has a different time value of production, different shape of that production of energy, well, that probably will provide a capacity benefit to the system. It will provide energy at times when energy couldn't be provided by other generators, say. But after you put more and more and more of that same thing in, well, the capacity value erodes naturally because now you just have more of it. There's less diversity than you had before.
That makes sense.
But there's still a capacity benefit. So I'm sorry, this might have been a little confusing the way I phrased this. These are still benefits. There still are net benefits, but the per megawatt benefits drop off in how impactful they are.
Thank you. Thanks for that.
Yeah, of course. Thanks for speaking up.
Travis, and one question came in the chat. I don't know if it's for you or Sahom. Maybe we just touch it quickly. In the study process, were the NERC planning criteria addressed, specifically N-1/-1 contingencies?
They were. Yeah, I don't know, Sahom, if you want to take that.
Primarily we use the N-1 criteria and check with Shanawaz on if there was any specific N-1 that we had used, but primarily we based our studies on N-1 contingency.
I think we probably should mention that, you know, there may be a max in feed limit in CAISO or Bonneville, sort of a single source contingency limit that they put in place that we did not necessarily, you know, include that. We didn't necessarily limit our topologies. You might have noticed that already, if that's where that question is coming from. You know, I just showed you 2,600 megawatt lines, you know, those 2,600 megawatts may exceed max in feed limits that currently exist on the system. This is a conversation in the Northeast as well. And folks are considering, you know, what it would take to change that limit. So we didn't apply those hard limits here. We didn't say like, oh, you can only have 1,500 megawatts on a cable or any N, you know, we didn't do that, but we did look at N-1.
Okay, I'll run through the evaluation of the first two scenarios. So remember, this is looking system at the system-wide scale, and right here we're comparing the difference between the benefits and costs in the HVAC radial connection case. So it's 3.4 gigawatts installed capacity, and then the baseline of the 2030 ADS. And just moving from right to left, this is like a waterfall plot where it just shows the economic value kind of stacked up again. So the positive ones are in blue, and then when there's a cost associated, it's in the reddish pink color. And then way over on the right is green, which just shows the total or net benefit or cost. In this case, it's a benefit. So I'll just walk through from right to left without going into too much detail, but you see benefits for reduction in production costs, which is the energy cost. There's a capacity value added for the addition of the offshore wind. And then the whole next set, these are some of the electric system benefits. They're relatively small in the general order of scale. So regulating reserves voltage support, all pretty small costs or benefits. And then the two costs you see towards the middle, transmission expansion, transmission reliability, this is where you bring in the cost of actually developing the transmission infrastructure to make the interconnections or address impairments or contingencies. I'll skip over a couple and move over to criteria air pollutants and CO2 emissions. So this is system-wide. We see reductions, actually pretty significant reductions in criteria air pollutants and CO2 emissions. This is because the addition of offshore wind changes the dispatch of the WEC system as a whole. So we see reductions in emissions across the board. The resilience case one, that's looking at when a heat wave occurs during a drought year, and then a wildfire shuts down KOI. So you see a little bit of benefit there in this case, because it reduces the amount of unserved load because you have offshore wind interconnecting. Then the next two red bars going down, this shows the CapEx and OpEx for the offshore wind plant. And then that results with the next net benefit shown in green. So we see here, so that's kind of the main plot here. We show the map on the left so you understand what the scenario is talking about. And then we show a sensitivity analysis up in the top right, that just is if you change some of the factors. So if you change some of the cost factors of HVDC, if you change the probability of the resilience events occurring. And one of the key findings I think that Travis had mentioned was in all cases and all sensitivities, there was a positive value from this sort of scenario. And we're going to go into a lot more detail about each individual bar. So I'll just kind of leave it there, unless Travis, you have anything to add, and then I can go to the next one.
That was perfect.
Okay. Yeah, so we'll see a pretty similar structure here, except there's a few key differences. One being, so this is the HVDC radial. So this is a lot more offshore wind installed off the California Oregon coast. So with HVDC radials, you see a significant increase in costs right there towards the middle of transmission expansion. This is just because you need many more DC interties, you need some DC converter stations, and this increases the cost. So you'll see kind of if you followed this all the way from the right to the left, the net benefit actually here is slightly negative in the base sensitivity case, showing that there's actually a slight cost overall for installing the system. But if some of the assumptions are slightly changed in terms of resilience events or some of the cost factors, this can actually shift to be net positive as well. And then, yeah, next slide, and Travis, you can cover the backbone if you like.
Sure. Yeah. So here's what happens when you add in the backbone. What we end up seeing is, and again, this is the same. So the plots are made for the orange row here. So the cost of carbon of $89 per ton, 50% chance of this 3-day heat wave in the Southwest every year. So every other year that happens, I guess. And then the 25% increase in the DC component cost that we have from that JEDI model, which is really land-based. And so what we see is here, and this is the same set of parameters that were shown in the last waterfall, but now you've just implemented the backbone. There is still a pretty significant transmission development cost and some reliability upgrades that are incurred. And then also voltage support needs are part of building out the system to deliver this amount of power, but you see significant energy and capacity benefits, actually significant growth in the capacity benefits from the radial HVDC case alone. And then growth in the criteria pollutant and emissions value, and then overall a net positive annual benefit, annual value. And that corresponds to a benefit cost ratio of 1.088. And you can see how these vary as we vary the various parameters. So there are some instances where, you know, if we double the HVDC transmission costs, we see that these business cases do not close. But if we, and by the way, that's if we maintain the same cost of carbon. If we increase the cost of carbon or increase the annual probability of a heat wave, then we see positive business cases for this backbone. And these business cases are not typical business cases, right? These are system-wide valuations. And then here's the increment. So here's, if we just isolate, so this was all compared to a base case, right? All these were compared to that base case, which was, we talked about, which was built off the ADS 2030 with additional VRE added. Well, now the comparison is between, in this chart, the waterfall is between the MTDC backbone and the HVDC radial. Same amount of generation, so very little energy improvement, right? Huge capacity improvement over these two. So this is what the backbone is buying you. Way more ability to send the power north, in particular, and we'll get into that. And then actually a reduction in this case in the transmission expansion costs because there are less of those converters incurred. You might have remembered that we use more of the AC hub in San Francisco for the MTDC case because we saw that looping. So that's an improvement actually between these two cases. And then sure, you know, because you're wheeling the power a little bit better and the system is using this asset, then you get further reductions, and even without any more offshore wind at all. So you're still seeing improvements in CO2 emissions, criteria, air pollution, and some resilience value in this case too. We'll get into that because the system is using this resource, not because there's more offshore wind included. So the net benefit here is that's the $1 billion that we talked about before, an annual net benefit. And then Mark made this great chart that looked at the per megawatt values. So I'll just quickly, just because we're running a little short on time, this goes back to that statement we made, how these erode over time. So if you just look at energy value per megawatt of installed capacity, you get this around $150 million. I think that's $150 million. I think no, $150 billion in terms of energy value. But if you go from HVAC radial to HVDC radial, you see a reduction about 50% of that value per megawatt. It's still positive, but it's just not as impactful per megawatt. And then the same thing happens with the MTDC backbone. The capacity drops off even faster with the radial, but then it's restored a bit by the backbone. And some of these costs, you know, increase as well. Particularly when we think about transmission expansion costs go up quite a bit, right? Per megawatt. You're not shocked by that because we've built out the whole HVDC system here. But then even the congestion value, you know, goes from actually a net positive to something that's a cost that's significant in these two future scenarios. A lot of that has to do with just flooding it with so much offshore wind. So that, yeah, we'll keep moving here. Any questions? We're about an hour in. We still haven't shown you a lot of the analytical pieces, but which we want to get to, but I want to pause here, Jason.
Yeah, thanks. We do have at least some comment questions here, pulling those up. Chip says, in the study process, were the NERC planning criteria addressed, specifically the N-1 contingencies?
I defer over to Sahom. I know we did N-1. Did we do N-1
We did only N-1.
Not to specific -1.
Okay, we just did N-1.
Thank you. And Theodore had questions, but he's also got his hand raised. Theodore, go ahead and take the floor.
Hey, thanks, Jason. Travis, this is fantastic stuff, and to you and the team, this is great work. So thanks for moving the base of knowledge forward so significantly here. Question on slide 20, and I'm always looking at this with an eye towards how's the slide going to be misread. So, your thoughts about maybe how this could be clarified, and to make sure I'm not misreading it too. So as I go from left to right, I would hate it for a policymaker to look at this and say, oh, HVAC radials, 250,000 per year, a megawatt, kind of the benefits better here. We should just do a bunch of radials, right? And as I looked at this, I thought, well, if the total megawatt number was attached to each of these columns, that would be really important, because of course, if you were going to do the big giant system with just AC radials, well, now I'm building huge offshore upgrades, and that number probably starts to look a lot worse than the MTDC backbone. So trying to apples across this chart, and just something to give some thought to, so it doesn't pop up with the wrong takeaway.
Great feedback. We will make that change. I appreciate it.
I think, so Larry had a question, is there any mechanism to monetize the reduction in criteria air pollutants? I believe Mark has answered this. The criteria air pollutant reductions are monitored based on their public health benefit. EPA published $ per ton for NOx, SOx, and particulate matter 2.5 through their bin map program. We use these values specific to states within WEC.
Yeah.
So reductions are monetized, not monitored.
We don't have a way to monetize that stuff today. I mean, we can have a whole conversation about that probably, Jason. Maybe there should be a way to do that. But outside of some carbon pricing, that's only part of the WEC, but not everybody's doing that. So we didn't include that directly, although the PCM does put that out, the ADS does that, but we focused on taking the tons of emissions and thereby the reductions in this case, and then monetizing it through the EPA valuation.
Thanks. And finally, Nora asks on slide 19, can you confirm which net benefit is being shown? Is it the benefit of the HVDC over MTDC?
It's the opposite. So it's the benefit of the MTDC, so the backbone, the more coordinated system, over the uncoordinated radial feeds, even though they are HVDC.
Great. I'm not seeing any other questions at this time. Back to you, Travis.
Cool. Thanks, guys. Really appreciate the feedback also. So at this point, we're going to show you some results that went into those plots. We want to kind of give you bottom line up front, but it's important for you to see how we got there, of course. And Lee is going to take it now.
Yeah, hello everyone. So yeah, we are illustrating the power flow from the PCM using these two-sided violin plots. So you can see from the violin plot, we have two-sided. The left side will be our reference case, and the right side will be our target case, which is offshore wind case. And from both top to bottom, we have the maximal, different percentile, the median, and the minimum value. Yeah, and these values are very important to help us identify what's the power flow on different passes. So on the left side, the base case is green in our next few slides, and the right side, the offshore wind, is blue in our next few slides. Okay, next one, please. So yeah, in this page, we show two different cases. The first one, the top three figures, we show the base one, which is ADS 2030, which is our 2030 HVAC radials. So we choose three different passes to show the power flow, which is pass 5 from Washington to Oregon, and the path 65 plus 66, which is PDCI plus COI, and the path 15, which is the connection between North and South California. And the second case, we choose base 2, which is H2030 plus HVDC radios. And our base 2 case is our ADS 2030 plus 35 gigawatt VRE. And our Oregon scenario 1, which is to 3.4 gigawatt installation, and also CAISO transmission planning, including the Collinsville station. And based on this wiring plot, we can conclude some major findings. And so in these two cases, both scenarios will reduce energy import from Washington to Oregon. Via this path 5, since we install more offshore wind on the side, and we don't need more energy import from Washington. But in the 2030 HVAC radio, we can see more offshore wind in Oregon increase the California energy import from via this path 65 plus 66, which means more energy flows into California through this path. But when we compare the 2030 plus HVDC radios, we can see since we also install some offshore wind in North California, so we don't we reduce the energy import via this path PDCI plus COI. And also we will have a reduction of the power flow from southern to northern California via this path 15. So these are the major findings in these two cases. But in the next slide, we will also show how the MTDC backbone will change the story. Okay, next slide, please. Yeah. So with this and these three figures shows the left side will be our 2030 plus HVDC radios, and the right side is our MTDC backbones. So we can see the MTDC change the story. So compared to our previous 2030 plus HVDC, so our scenario MTDC increased energy imports from Washington. So which is very important, although we install offshore wind in Oregon and California, but with MTDC, we still need more import from Washington to support California. And in this case, the MTDC backbone, and we can see the bottom left figure, which shows the subtop to potato flow circuit 1, which is a very important link on our backbone. So with this link is the connection of north and south. So when you are trying to push power from northwest to California, you have to go through this lane. And we can see with this MTDC, there's a significant reduction of power both PDCA plus COI and the southern to northern California on path 15. And so we can see from the yearly load duration curve on this MTDC backbone, we can see the MTDC backbone mainly sends southbound power flow, which is from northwest to California. But in some hours of the year, there are also reverse power flow from south to north. So yeah, this is the major findings on this MTDC passes. Yeah, that's it.
Great, thanks, Lee. Okay, so now this is how we modeled capacity. We used this associated system capacity contribution metric, which we adopted from the Northwest Power Conservation Council, and we worked closely with, we've run this by John Fazio and his team. John has since moved on, but into retirement, I think, but we hope to talk to him later this week. But he consulted on this early application of the ASCC method. And Jen and Stephen have been knee deep in implementing this, but maybe just maybe we'll have them answer questions, and I'll go ahead and present this for now. We did modify the grid view software. They did, I should say, and made some significant modifications so that we can use 18 different years of hydropower, wind, and solar profiles. And we also included forced outage rates and D rates particularly for wind energy, resources and solar energy resources as a function of temperature. A lot of people don't know that when you get above, if you're at 100 degrees inland, your wind park, those wind turbines are not probably operating at their nameplate capacity, even at nameplate wind speed. And that has to do with how hot they get and the cooling systems that are installed on those turbines. On an individual turbine basis, that's not a big deal. But when you think about an entire park or collections of parts, and you start rolling out 400 megawatts, gigawatts, it becomes important. So we wanted to make sure we had captured those effects. And then we also had to scale the loads in California and in the Northwest to show unserved load so that we could apply this method, because the systems have a fair amount of reserve margin built into them. So the scaling goes like this. It's actually not 100% scaled for the 2030 case in California. In the Northwest, we have to scale closer to 110%. In the 2030 beyond case, we have a scaling of 104% in California, 126% in the Northwest. That applies to both the radial HVDC and the MTDC cases. And then what we do basically is we run 8760, so all hourly dispatch for a full year. And we do it for many times for many different weather years. And for every one of those combinations of the weather years, we run 30 different trials, varying some of these force outage rates and D rates and other variables in the model, such as transmission transfer capability, things like that. And then what you end up with is you take the worst hour, the peak hour of unserved load from each one of those trials, and then we make these composite curves, which are load duration curves, and they're called curtailment curves here, but it's basically the worst hour from every simulation. What was the highest amount of unserved load in every one of those simulations? And then you sort that curve from largest to smallest, and you plot out what the base case looks like in red, and then you add the wind, and you see what is the shift. There should be, if you're providing capacity benefit, you should see less unserved load in those peak hours, and so this curve will shift down vertically. And near the zero crossing, the authors have argued that's where you should take the ASCC metric, and that's your capacity value. So in this case, you drop peak hour curtailment by 480 megawatts. So your capacity credit is 480 megawatts divided by 3,000 megawatts installed, and that's how you come out with what the effective capacity is of that resource. The one we've made a couple changes to this method. First of all, we've put in a lot of different weather years and more variability into the model, and so we explore convergence by exploring the top N unserved load hours from each trial. So not just the worst one, but maybe the worst 3, the worst 5, the worst 10, the worst 20 hours from each trial. And then we also looked at not just taking the results from one offset, but looking at maybe a series of offsets and averaging them. We did that for different sections of the curve, 25% back for the overlap, and then all the way halfway back for the overlap, or looking at the entire curves where they overlap in terms of unserved load hours. So not throwing out this part where the project case doesn't have any unserved load, but everything back from there. And we just did regression statistics on how the ASCC metric changes. And these were the trends we observed. There's a lot of data on this chart, but I will just give you the high level, which is that in general, we're running 30 trials per weather year. We see that about 10 trials per year seems to give us some pretty good convergence in terms of the average ASCC measured from the last 25% of the hours that overlap near the x-axis, and then also looking at the standard deviation trends. And so this graphic in the upper right shows you that if you look at these two curves, so here's the blue curve, that would be the base case, and the orange curve has the offshore wind included. And if you were to take the 25% average ASCC, you go back from the X crossing of the project case, and you go back 25% of the hours of unserved load, and look at the increments between the two curves, and then average those. And that's how you get these dots. Those are the average numbers. And then we also do that by going back 50%, and then finally going back the entire time and seeing how the values change. And in general, we concentrate on that zero crossing, because that's the point of loss of load probability, and we focus on we try to find scaling so that crossing happens around 10%. That's the loss of load probability of 10% is a metric a lot of planners still refer to. it's not cast in stone, say, but it's something, a useful metric to look at. And we see, some pretty robust capacity in scenario one, in this HVAC radio scenario, and then erosion of that, and then a restoration of that, particularly in the Northwest. And I'll show you the plots now. So here are the plots that show the ASCC trends for this offshore wind resource off the coast of, as measured in the California zone in the model, and then also separately in the Northwest. And so California on top, the Northwest on the bottom, and then the three different scenarios, the HVAC radio on the left, in the middle, HVDC radios, and then finally the backbone on the far right. And you can see early on really significant capacity value. I mean, really high. The offshore wind, and we looked into this, offshore wind is howling when California needs the energy in the summer. So that it just happens to be a natural complementary that's even stronger than the Northwest. And then when you go to radio connections, that drops off. And of course, you're adding more megawatts of the same resource. So as we said before, that's part of the reason why it drops off, because now, you even have some megawatts in your base case. But then the MTDC restores it quite a bit in the Northwest by letting you move power to the north. So this is a significant finding from this work, is that the capacity contribution is quite strong early on, and it can be kind of preserved to a degree with coordinated transmission. Okay, over to resilience. So Lee, this is you.
Okay, for resiliencies, we consider three different cases. The case 0, we choose a very extreme case, so which is a very low probability of occurrence. So we modeled 2 weeks heat wave at the end of July, and load increased by up to 40% in wake system, especially in California and Southwest. Besides, we also consider PDCI plus coil outages, which means we will lose 8 gigawatt southbound transmission capability and about 7 gigawatt northbound transmission capability. And in case 1, we consider a normal case, which means we only consider 3 days heat wave and only 20% load increase in California and Southwest. And also we will have the PDCI plus coil outages. And the third case, case 2, we will have a similar setting with case 1, but we will consider the drought without drought to see the benefit of the MTDC. And the reason why we choose the end of June is we check the historic data from the cooling degree days, and we see on July 2018, there's a coincident heat wave in both California and Southwest. So yeah, next slide, please. So in all related cases, one major metric is the unserved load. So from the left side, the first figure, we can see that in case 0, which is the extreme case, we have different amount of unserved load. And we can see more offshore wind and renewable generations can mitigate the unserved load. And of course, with more offshore wind and all MTDC backbone, we can mitigate the unserved load more. And in case 1, normal case, we can say the heat wave happens especially in these 3 days, but when we check the wind profiles on these 3 days, so we have limited load generation, which shows in the right side. So in the red box, we can see the yellow curve is the wind generation of the all offshore wind generators. And we can say during these 3 days, we have the heat wave, but we don't have enough wind generation. So we will have limited MTDC backbone benefit during drought as the black curve. So we have limited power transmitted from this MTDC backbone. But for the blue curve, when we don't have a drought, we have enough hydro generation in Northwest, and even we don't have wind generation during 3 days, but we still can transfer about 2,000 megawatt power through this MTDC, since we already lose PDCI and COI during the heat wave and wildfire outages. So we can still use this backup path to deliver power from north to south when we have enough hydro generation. So this is a major finding and the extra benefit of this MTDC backbone in our resiliency cases.
Thanks, Lee. Yeah, it's important for folks to realize that we kind of stumbled upon this, that if you pick a resilience event, which happens to coincide with a really a lack of wind offshore wind production, which is what happened to us here. We're like, where is the resilience value? It was only when we were also running this with drought. When we took the drought away, then when there was enough excess hydro to use the MTDC backbone and show some resilience benefit, even when the offshore wind wasn't producing. So this helped us realize that we need a lot of multiple scenarios to understand resilience value. You can't just do one. That might seem obvious, but they each have to have their their probabilities as well. Okay, thank you, Lee, for that. So now a few comments on costs. So I think, and there was a question earlier, Mark, I think you're taking this.
Sure, yeah, I'll take this and I'll be brief because I know we're shorter on time. This is showing an overview of the cost for transmission, expansion, and interconnection for all three cases or scenarios. So we see maybe just the top line is the kind of the number you'll end up taking away because big costs, so the HVAC radial connections are about $700 million for the 3.4 gigawatts. And then the radial and the backbone, 15 million for the HVDC radial and 14 billion, and then 14 billion for the MTDC. The next several slides are going to walk through some of the details of where those costs come from. And I'll just note that the actual costs, like we use a set of assumptions and run it through a JEDI transmission model that really helps us spit out the capital and operating costs for these systems. And so this slide plus the next two will just walk through the different line items that make up that total. But I'm not going to walk through them in detail because there's probably some other important things to cover today as well.
Yeah, but maybe just to know that these new 230 kV builds are quite expensive, and those are modeled in the HVDC radio case. In the HVDC radio case, keep in mind that these 500 kV DC interconnections do also account for converter costs. So, and those are quite expensive. So we look at SATSOP. This SATSOP line is not just the line; it also includes two converters. Okay, so that's true for this full HVDC radio build out, all the converters that are shown in this graphic. Then the reliability upgrades are these, which are mostly restoring 230 kV capability or enhancing it. I think some of these are new builds though, new 230 kV builds potentially. Shanawaz, correct me if I'm wrong there.
Yeah, there are some circuits where we have some lines where we have had to add additional circuits instead of reinforcing the existing one.
Right. And then with the MTDC backbone, we end up with, remember, a few less converters needed. So you can see here that in Martin San Mateo, it's I should say 230, sorry, 230 kV AC connections. So that shaves quite a bit of cost in the overall, so up to $1 billion. And then also remember, that was true in also scenario 2 that Trojan does not have a DC connection anymore. This is actually an AC connection. Sorry, there's a few errors in this chart. I will clean up. Okay, and then, so guys, we have 5 minutes left before people are going to have to go. I want to make sure we present things that are impactful to folks. Yeah, so let's quickly go through. So Sahom, I know you were going to give this slide. The point being that we ran multiple types of analyses to come up with these reliability upgrades.
Yeah, yes, Travis, I think just wanted to kind of reinstate that, like for this particular study, the framework that we put together looked at like from years to months to minutes, seconds, and then sub-seconds. So kind of an all-in approach for looking into the various aspects of the integration of the offshore wind and its impact on the power grid. And Shanawaz can go over some of the results that we found for all the 3 different scenarios. Shanawaz, do you want to kind of cover this?
Yeah, so yeah, I mean, for the HVAC radial, which only consisted of flows into northwest, we considered about 4,355 contingencies. And then for the HVDC radial and for the MTDC backbone, we also included the contingencies in an analysis from Northern California. So like each of them had like different unique violations. We were only trying to look at violations which were above 115 kV level, violations which were only in the Northwest and Northern California. And using that, we identified some 230 kV upgrades. For HVDC radial and MTDC backbone, a lot of those upgrades were similar, just a few of them were different. But yeah, the cost for both of these, for all the upgrades here has been taken into account in the valuation analysis. And yeah, I mean, there were a lot of violations. Even the base case contained some violations which we tended to ignore in our analysis, because those we assumed that would be fixed at some point of time. We were only trying to look at the new violations which were introduced into the system because of the additional wind that we are bringing in, as well as our HVDC radial builds and the MTDC builds. Yeah.
Okay, Mark, I think you should cover the emissions quickly, and then maybe we'll pause. I can stay on. I know folks, I'm sure everybody can do that, but yeah, Mark, can you cover this one? I think it's pretty impactful.
Sure. Yeah. So this is a plot just showing the three scenarios and the total reduction in emissions between that scenario and the base case. The stacked bar really just shows the variability in how the carbon emission reductions can be monetized. So the bottom darkest bar just shows what are the current market payments that are reduction in market payments associated with carbon that are avoided in the offshore wind scenarios. And this is for a very limited subset of areas in the WAC that have active carbon markets, and this is accounted for in the production cost model. On top of that, the next bar, that's really just showing the baseline of what the Biden administration has published in terms of the social cost of carbon. So this takes into account all of the impacts associated with the changing climate and how each ton of carbon dioxide emission contributes to that. So that's kind of the next stack. And then the highest stack is really the EPA's estimate of the social cost of carbon, which many experts think is really a more robust methodology to really account for the impacts nationally about carbon emissions. So I guess the takeaway here is there's a wide range in how those can be valued, and it would significantly impact how you kind of see the big picture of offshore wind at the system scale.
Yeah, thanks, Mark. And then the OpEx and CapEx come from prior studies that we've just scaled up. It's pretty straightforward. And then we have a bit on transient stability. Before we dive into this, because folks might have to hop, this is a pretty detailed, it's really interesting work. And I will say that we ran into some brand new stuff here that we don't think has been done. And Samir is on the phone here, has led a lot of that work for us. But before we go there, let me pause here for any additional questions in case people have to drop. And I totally understand if they do.
Travis, we did have a question here from, if you're following the chat, Theodore did have a recommendation on slide 30, and then Jason Searman asked, did the MTDC assessment pick up any non-offshore wind power transfer from north to south? Wondering if any power flows from Alston heading south.
Definitely.
Yes. Yeah. I can take that. Yeah, I mean, there is a lot of power which flows from north to south. I would say that for majority of the hours of the year, we see that the flows are from north to south. It's only in summers that we see a lot of south to north flow. And for non-offshore, yes, there are few hours in maybe February, March, and April that we see that there is not a lot of offshore wind generation, but we still see our MTDC backbone being utilized to a very high capacity. Yes.
Yeah, well said. And I will say that the flows, when they go south to north, that's how we get the capacity value in the Northwest. That's the big change with the addition of the backbone in terms of the capacity, the ASCC trends. We looked into that and tried to understand, well, why is the capacity value increasing so much in the Northwest? Well, that's because we're benefiting in the Northwest of having that MTDC topology even beyond the offshore wind power flows. We're getting solar from the Southwest to serve load peaks.
So Travis, it's a couple minutes after 11:30 here, and perfectly fine on my end to continue. And for folks who want to stick on, stay on the line. Let's do that. Anybody peels off, that's perfectly fine. And of course, the recordings are available on the website, and Travis will be making the slide deck available at some point hopefully in the near future.
Yes, sir.
So
Excellent.
why don't we take maybe 7 or 8 more minutes, 40 after, and call that good.
Okay. That'll work well. Okay, thanks, Jason. So over to you, Samir. Oh, maybe this is Sahom taking this one, and then to Samir.
Yeah, maybe I can just kind of start the conversation on this. So for transient stability and frequency response studies, I think the primary reason we headed this way was to make sure, like, after all the analysis through production cost model and the contingency analysis, looking at AC feasibility, we also want to make sure with respect to dynamics, the system is stable, and any kind of major disturbance affecting the Western grid, and with so much of renewables and offshore wind, especially for the 2030 plus cases, the HVDC and the HVDC backbone, that there's not a significant impact on the system frequency stability. And this was, as Travis mentioned, like, we ran into a lot of things while working on this. First thing is, like, for 2030 ADS models, there are no WEC dynamic data available. So we do have the master data file from WEC, and what we do is, like, we kind of clean that up based on the resources that are newly added, and try to get a good response from the base case before we get into the studies. So for the scenario 1 or the HVDC or HVAC radials, and the scenario 2 with the HVDC radials, we were able to get more or less good results with respect to frequency response. We performed the single largest contingency outage in the WEC, which is the outage of 2 Palo Verde resources, and look at the frequency response following that event, and how the performance was from the offshore wind. We did take the heavy load and the heavy wind cases for these studies. Like, this require a lot of fine adjustment, and so we would love to do these studies for multiple scenarios and multiple snapshots of the system, but due to time constraints, we restricted ourselves just to those cases. And the primary takeaways were, like, for scenario 1 or scenario 2, we did not see a significant impact of the offshore wind on the primary frequency response. The frequency nadir and the frequency response were well within the standard ranges that is observed for WEC. And of course, like, with further improvement in the dynamic models, as we are working on different projects that are looking to do this kind of simulations for the future grid with those high renewable cases, we will have better results in the future for sure. But these do give us some sense of clarity and regarding the frequency responses, and we'll go over some of the results in the next few slides. Regarding the scenario 3, which is the HVDC backbone MTDC case, for that one, we really ran into a lot of issues and challenges, primarily because the existing tools and softwares that we have, like for the GPSLF or the Siemens PSSE, even PowerWorld, they don't have like a very well developed model to simulate MTDC in dynamic simulations. So for that, we developed a user-written code in PSSE in Python, and that was used to simulate the MTDC. However, like, due to time constraints, again, we were not able to translate that into the full WEC model, and for that we used a mini WEC, a reduced order WEC model with the increased load and the renewables and the offshore wind being modeled, and we'll kind of go over what results we found there. It's still a work in progress, and hopefully in the future we'll have better results, And this is kind of just for the industry to kind of see some of the modeling challenges that are primarily existing to kind of simulate and showcase some of these cases, especially if you're looking at modeling the MTTC for offshore wind resources. So yeah, so this is for our HVAC radial case. This is like with 2 Palo Verde outage. You see some oscillations there, and that's primarily because some of the models do need further tuning, and we did use a full VEC case for this particular analysis. What we observed, frequency nadir of 59.8 hertz following the 2 Palo Verde outage, and that's very much within the benchmark results and the performance requirement for VEC system. Going forward to the HVDC radial, we see kind of similar response and not a significantly bad frequency nadir as well, with the performance metrics for the frequency response also within the limits for the VEC standards. We also observed like the responses and the megawatt output of the offshore wind plants following the Palo Verde outage. We see some minor oscillations there on some of them, but other than that, they are pretty much flat and are stable with the performance from the offshore wind resources. Next, we go into the MTTC modeling, and this is the mini VEC power flow case that I mentioned. And here we increase the load to 164 gigawatt. Originally, the mini VEC case was designed in 2008, 2005 timeframe. So the load was almost like close to 100 gigawatts, much less than the 2030 load. So we did scale up the load, and we did add like the 35 gigawatts of renewables before we added the offshore wind. And I'll invite Sami to kind of give us a brief description of how he was able to model the MTTC piece using the user-written script that helped us to do some analysis for the mini VEC case.
Thanks, Mo. Good afternoon, everyone. So while integrating this MTTC model, so first of all, like Soham mentioned, this was a custom-built model based on like we have leveraged this model from another project here at PNNL. It's a track program, and basically what's this model is based on the reference shown on the slide here. This model is custom-built model built as a Python script, Python and Fortran scripting, user-defined model in which it contains 2 parts, both the power flow modeling and the dynamics modeling, in which the power flow model is, since we have the DC part also on the HVDC in the MTTC model, it's a sequential power flow algorithm which we have leveraged to conduct the power flow simulation originally. So it's basically at the injections on the mini VEC at the point of interest we have. We try to in that particular algorithm, it's a sequential AC DC power flow where we update the AC buses and then go back to the DC system, and then we solve the voltages and the power flows in the DC system, and then go back to AC system until we reach the convergence at one particular location where it's called a DC slack location generator, one particular location on the onshore wind. And then once we get the power flow results, the dynamics consists of some outer loop and inner loop current control loops, where we try to control the currents. Either it's like a power AC injection or DC voltages. These are the variables that we try to control using the dynamics. And once we have all this modeling capability, the results, we have done some tests such as fault at Palo Verde bus, and to benchmark the model. So in this result, as we can see, when we ran a three-phase fault with some fault resistance, not a bolted three-phase fault, but as you can see, the system response is pretty stable, and the field winding voltages respond accordingly. So as the voltage drops at its terminals, the field winding increases to compensate for that. So the response is pretty good. Next slide, please. So we also ran a frequency event by tripping a generator at Bridger. So this is a location in Wyoming, and it corresponds to bus 74 in the Minivex system. And as you can see, once we have a flat start until 5 seconds, and at 5 seconds we try to trip this generator, which is 214 megawatts, and the system does recover, but we have some issues with the model running it for longer time for frequency trip events due to some numerical issues. We are still trying to smoothen it out. So what we have observed is that a nadir of 59.96 hertz here, so not much significant impact on the frequency response. And we also try to run large power outages, but as I mentioned earlier, due to these numerical issues, we couldn't get that. So, but we were able to get some results similar to similar amount of generation trip that we did here at Bridger. So we do have some results in the backup slides. Yeah. Oh, over to you, Travis.
Okay, thanks, Samir. That's great. Yeah, so that's new work. Certainly, the MTDC dynamics is totally new. We had to write our own codes to even get this far, and there's more work to do there. But glad that Samir and Sahom investigated it, because the last thing we want to do is propose something that completely destabilizes the WEC, for example. That is a cost we would need to account for, and we're not seeing that. Signs are not showing us that would happen, but we would need to do additional work in the future to improve the models, the dynamic models, and to know just to further resolve the numerical issues we're seeing. But there's nothing that shows us that those are that's a destabilizing increment to the transmission system. You've already seen this slide. A few other things we talked about: capacity and resilience. I'll let you read this later, but basically with resilience, the key is that you need many scenarios. We ran a couple. We could see future work in further building out the resilience scenarios, and along with their, importantly, because a lot of people talk about resilience, but when you want to evaluate, you have to have confidence as to how often that event will happen. It's not enough just to say Cascadia subduction zone. You have to know, well, okay, what am I going to count on in terms of a probability to turn that into an annual value? And that has really been the sticking point for us. We came up with a lot of unserved load, but to actually credibly defend how likely it is to happen is the challenge. So I could see more work there, and we've pulled from various sources to inform the work that we showed you today. And then, of course, cost data. We need better cost data. We try to do a sensitivity study here to capture trends, but it'd be better if we had a floating offshore with specific transmission cost information. And I know others are working on that, and we're working on that on the West Coast study, the WOW-TS, so that'll be something to come. Expanding the regions of consideration, doing a true co-optimization, so we're not just restricted geographically. Like here, we had to stay within Coos Bay and Eureka. That was part of our scope. But if you could just do the West Coast wide and say, okay, now tell me, given all the POIs available, really where are the best places to put this resource and what transmission supports it, that would be an improvement upon this work and an extension of this work. I'll let you read more of this, but I think applying this to different this bottom up and system wide strategy to other interesting transmission planning problems. One came up in the chat, subsea cable into LA. That I think is another place where something like this could be used. So we're over time. I'm going to stop. I will be sure to get the slides out. I can stay on to take any questions. I see we still have some people on. So Jason, over to you.
Well, thanks, Travis. Clearly, the P&L team has done a lot of work on this. So congratulations on pulling all this together. And of course, we know that this is a stepping stone to future work. It's going to inform that. So all that much more important. I didn't see any unanswered questions in the chat. Let's just see if anybody on the line wants to raise their hand. Give folks a couple seconds here, ask last questions. Going once, twice, three times. Okay, let's obviously an accolade there. Good, great work. Okay, thank you, Travis. We look forward to seeing the results from the final slide deck. Let us know. We'll make that available to our participants. And thanks again. Look forward to hearing more about your next steps.
Thanks for having us, Jason, and thanks, Bill. Appreciate everybody for being on. Thanks for the feedback. We'll take it by email too. If there's something you didn't want to say now, that's fine. Please email me.
You did note the Theodore's recommendations on particular slides. Yeah, I think that those are important nuances that when we're presenting this material publicly, it needs to, as you and I have talked about this a long time, the all important executive summary and making that readable for our decision makers.
You got it. We will be going to a report next. Just we started drafting that, but all this content will go in a report. I should have said that. I'm going to send it to you, Jason, and you're going to take it to this group. So we would love your feedback on that on the draft report, but we'll make sure to include those. This is all hot off the press stuff you saw today. You're the first eyeballs on it. No one else has seen it. So congratulations, but it is a little rough in a few places. So thank you.
All right. Well, thanks everyone for participating today. Have a great rest of your afternoon.
Take care.
Bye-bye.
Thanks, everyone.